Hi everybody, I hope this video finds you well. Today we're going to be taking a look at section 2.2, which introduces some operations on matrices and sort of is generally talked about as matrix algebra. To begin with, we're going to discuss the idea of adding matrices. So how do we sort of perform matrix addition? So with matrix addition, we're going to use this definition. So we're going to sort of let A, B be same size matrices. So they're going to both be m by n matrices. And we're only able to add matrices of the same size. So that is a limitation to matrix addition. You can only perform it when you have same size matrices. Then the matrix A plus B will be m by n, so their sum will also be an m by n matrix with elements A plus B ij is going to be aij plus bij. So in other words, when we do matrix addition, we do it element-wise, so element by element. As a quick example of that, right, let's have A be the matrix 2, 3, 0, 4, and B be the matrix -1, 5, 2, 3. Then A plus B would also be a 2 by 2 matrix, and it would have elements 1, 8, 2, and 7. And of course, 1, 8, 2, 7 comes from simply adding component-wise. So this 1 is coming from adding 2 and -1. This 8 is coming from adding 3 and 5, so on and so forth. So matrix addition, very straightforward, just going to add the matrices element by element. Of course, because we're going element by element, it does have that limitation that the two matrices must be the same size. The great thing about matrix addition is using this definition, if you want to, you can show some basic properties of this, and namely, you can show that it has the same properties as normal addition of numbers. So, first property we should talk about is that it is commutative, meaning that A plus B as a matrix is the same as B plus A. You can think about how the proof of that would work. You would simply show that the components in the ijth element of A plus B is the same as the ijth element of B plus A by using the above definition. And it is also associative, meaning that if you have A plus and then you decide to add B and C, that is the same as first adding A and B and then adding C. Remember that another way of thinking about it being associative is just simply saying that those parentheses are unnecessary, that A plus B plus C is exactly that, right? It doesn't matter the sort of when you decide to add those matrices. You can add A and B and then C, or you can do B and C and then A. So those are both properties, commutative and associativity, that we have for normal addition, and they also hold for matrix addition. All right, let's talk about some multiplication. When we talk about multiplication, though, we're going to actually start with a very basic form of multiplication and sort of work up to a more advanced form of multiplication. So to start with, we're going to talk about scalar multiplication. So, scalar multiplication. This is how you're going to multiply a scalar, so a number, right? Possibly, most likely a real number, sometimes perhaps a complex number, but just a number onto a matrix. So we're going to have A is m by n, k is a scalar. So that means just a number, right? Could be real, could be complex, most likely just going to be a real number here. Then ka is m by n with elements ka ij is going to be k aij. Now, we already sort of gave away this definition of scalar multiplication in our sort of previous video where we talked about negative a and talked about how you just negate every component. This is exactly what the definition of scalar multiplication is saying. It's just saying that when you multiply a scalar onto a matrix, you multiply every element in the matrix by that scalar. What's an example of this? Well, let's have A be the matrix 2, 3, 0, -1, 4, 5. And let's have K be the scalar -3. So then -3a would be the 2 by 3 matrix, so same size. That would be -6, -9, 0. 3, -12, -15. And of course, every one of those values is coming from just simply multiplying the element by the scalar. So this -6 here is coming from taking the 1 element in A and multiplying it with that -3, so on and so forth. Scalar multiplication is very sort of straightforward here, and it does have some properties, right? So the first one that we should keep in mind is it does have the unit property. So if you take the number 1 and multiply it with a matrix A, sorry, that looks a little sloppy there. I don't know why my 1 is quite so ugly, so let's try that again. If you take the number 1 and you multiply it with A, right, what you're going to get is exactly the same matrix A. So that's the unit property. 1 times a matrix is, of course, that same matrix. 2, we have a distributive property. Right? The first distributive property is that a single scalar distributes over matrix addition. So if you take k times a plus b, then ka plus kb. So you can do the addition first here and then multiply by the scalar, or you can distribute the scalar onto both and then go ahead and do the matrix addition. Either way is going to be appropriate. Again, here we do have the implicit assumption, though, that a plus b makes sense. In other words, that a and b are the same size. We also have another distributive property. This distributive property says that you can also distribute when you have two scalars in a single matrix. So if you have k1 plus k2 times a single matrix A, you can do that as k1a plus k2a. So basically, this scalar multiplication distributes over matrix addition in both ways that would make sense. So those two distributive properties together make sure of that. And then finally, there is an associative property here. So if you have two scalars, so if you have k1 and then k2a, you can choose to multiply the scalars first, k1 times k2, and then multiply it onto the matrix A. All of these properties are basically just saying that this scalar multiplication acts as you would expect it to, which is great because we're trying to define the operations that we already know about, addition, multiplication, subtraction, etc., right? In a way that sort of extends them from just numbers into matrices. All right, so we've discussed these. For these properties, again, you could think about how you would prove them. You'd prove them element by element using the definition of scalar multiplication. We sort of mentioned, or I briefly just mentioned, subtraction, so let's go ahead and talk about that as well. We can actually define subtraction based on just addition and scalar multiplication. So let's go ahead and do that. Matrix subtraction. So what we're going to say here is if A, B are size m by n, then A minus B is size m by n with elements A minus B ij is going to be Aij minus Bij. So we're going to define matrix subtraction exactly as you would expect. Now, I do want to just make a quick note here. This isn't necessarily important to the definition, but it is important just sort of conceptually. You should realize that matrix subtraction isn't really a new operation, right? What we should note here is that A minus B is really just doing A plus -1 times B. So if we use the previous two definitions, matrix addition and scalar multiplication, we don't really need a new definition of matrix subtraction. It just simply is adding two matrices with one of them being multiplied by -1. So that's matrix subtraction. We can just talk about a quick example, right? We could have A being the matrix maybe 5, 0, -2, 3, 4, 6. That's a 3 by 2 matrix, and then B would have to be the same size for it to make sense. So let's do 1, -3, 0, 6, 4, -2. Then A minus B would be, again, just doing this component-wise. So our first component, 5 minus 1, would be 4. Then 0 minus negative 3 would be 3. Negative 2 minus 0 would be negative 2. 3 minus 6 would be negative 3. 4 minus 4 would be 0. And 6 minus negative 2 would be 8. So there's our matrix A minus B there. Okay. Now that we've talked about subtracting matrices, right, we can introduce a very sort of special matrix that sort of goes hand in hand with addition and subtraction. So let's go ahead and talk about what is called the zero matrix. So, zero matrix. The zero matrix of size m by n is simply a matrix entirely of zeros. So, in other words, the zero matrix is just a matrix where every element is 0. I will sometimes write this in notation as 0 and then sort of m by n if we're unsure of the size. Sometimes if we know that we're talking about a matrix, right, we'll sometimes get away sort of with loose notation as just a 0 when we know that we're not talking about the zero matrix as opposed to the number 0, but we do need to be careful there. Sometimes you guys will also see 0 sub n, and what that means is that's the zero matrix n by n. So the square zero matrix. And if we know we're talking about a square matrix, we only need to write one of the dimensions since we know that both dimensions are going to be the same. Now, there are some properties of the sort of zero matrix. So let's let A be m by n, right? And we've got a couple sort of properties that we want to discuss here. The first, right, is namely, as you would sort of expect, that A plus 0 of the m by n, as long as it's the right size zero matrix, is going to just be A. So in other words, the zero matrix serves as the number 0 would do, meaning that adding it doesn't change anything. The second sort of property is that if you take A and you subtract it with itself, you will get that zero matrix of the appropriate size. The third thing is, if you take the number 0, right, so this is going to be the scalar 0, and you multiply it onto the matrix A, then of course you will also get the zero matrix of the appropriate size. Now you'll notice that in this last one, we're being very careful with the notation. This 0 here, without any sort of subscript, is going to be assumed to be that scalar, whereas this guy over here is now a matrix of zeros, right? So this 0 here and this 0 here are very sort of different things. Okay, let's wrap up all these sort of basic operations by just looking at a couple examples of adding, subtracting, multiplying, doing scalar multiplication, etc. with matrices. All right, for our example here, let's go ahead and define a couple matrices. We're going to let A be the matrix 2, 3, 0, negative 1, 2, 5. We're going to have B be the matrix 2, 3, 5, 3, 0, negative 1, 5, negative 1, 6. And we're going to have C be the matrix 1, 4, 8, 1, 3, negative 2. So what we're going to do is we're going to evaluate, if possible, the following, right? So we'll try to do A plus C, A plus B, 3B, and 4C minus 2A. So let's look at A plus C. Is A plus C well defined? Well, yeah, right? A is a 2 by 3 matrix. C is also a 2 by 3 matrix, so they have the same size, so we can go ahead and add them. A plus C is just going to be doing that addition element-wise, so it looks like we'd get 3 from adding 2 and 1, then we'd get 7 from adding 3 and 4, and then 8 from adding 0 and 8. Then we'd get 0 down here from adding negative 1 and 1, 5 from adding 2 and 3, and then 3 from adding 5 and negative 2. So A plus C would be that 2 by 3 matrix. A plus B, well, is that well defined? Well, A, again, is that 2 by 3 matrix, and B is that 3 by 3 matrix. Those are not the same size, so this is not defined. So we would not be able to calculate a plus b because it's not a well-defined operation. All right, what about 3b? Well, 3b is just taking the scalar 3 and multiplying it onto everything in matrix B. So if we do that, we should get something like 6, 9, 15, 9, 0, negative 3, 15, negative 3, 18. Now you will notice something sort of interesting here, right? If you look back at matrix B, we can actually see matrix B as an example of a matrix that we've run into beforehand. It has sort of a special designation. This is a symmetric matrix. Its transpose is identical to itself. If you look at 3b, this is also symmetric. So you can sort of notice here that under scalar multiplication, right, that symmetry is preserved. And you can think about how you would prove that sort of in general. You could try to prove that if you take a scalar k and you multiply it with a symmetric matrix A, you still get a symmetric matrix. All right, let's go ahead and take a look at our sort of last operation here, 4c minus 2a. Well, is this going to be well defined? We can sort of look ahead and realize that 4c is going to be the same size as c, so it's going to be 2 by 3. And of course, 2a, or negative 2a, is going to be the same size as a, so it is going to be well defined. Let's go ahead and actually do this operation. 4c is going to be 4, 16, 32. 4, 12, negative 8. And then we're going to be subtracting 2a, which looks like it's going to be, getting ahead of ourselves a little bit there. It's going to be 2a here is 4, 6, 0, negative 2, 4, 10. Then we can go ahead and do that subtraction. So we get 4 minus 4 is going to be 0, 16 minus 6 is going to be 10, 32 minus 0 is going to be 32. 4 minus negative 2 is going to be 6, 12 minus 4 is going to be 8, and negative 8 minus 10 is going to be negative 18. And so there's our matrix, 4c minus 2a. So there we go, just some basic operations using addition, multiplication, subtraction, etc. In our next video, we'll go ahead and start talking about how to generalize multiplication so that we're not limited to multiplying a scalar with a matrix, where we can actually multiply matrices themselves. So we'll see that in our next video.